Okay.
Hi Ella, how's it going? Hope your flight went well. Okay, action.
What is that book?
What is that book?
Okay. So let me explain what this book is. So I used this for my Chem 1 students this morning because they had to look up the accepted value for the density of germanium, I think. So this used to be like a mandatory thing that you would see in any high school lab, any college lab, any research facility. So this was what the term BI, okay, before the internet, when you actually had to look stuff up in a book. So I know, shocking. Catherine's going, no, but yeah, like you had to like open up the pages, okay? I know, shocking. Nick's over there. Sorcery, okay? What is this wizardry you speak of, okay? So, and knows there's not incantations or anything like that. But it is cool because, I mean, it's just look how massive this is. So this was like the encyclopedia, all in one edition of any physical constant that you could possibly need relating to chemistry or physics, okay? Structures of molecules, atomic masses, densities, chemical formulas. For those of you that are, like here, this is how like you used to do like logarithms. So they have, instead of like typing it into your calculator, if you wanted the log of say 10, okay, this is how you would look up that value instead of just punching it into your calculator. And literally, like, here's the natural functions of, and this was big because, for example, this, like, if you wanted the 16 degrees, so this was the sine, tangent, cotangent, cosine. And this was important because this actually went out to 4 decimal places. Most of them only went out to like 3 decimal places. So if you were doing those calculations, you would actually, because number one, you were using the slide rule. Have I shown you the slide rule?
Yeah.
Okay, so if you're using that slide rule, you would go through and you would look up this number. And that's what you would use on that slide rule. For those of you that are math nerds, so this is a whole table of integrals. Like if you want to take the integral of sine squared x over cosine x, and it tells you what it is. So this was like all of the potential logarithm, or excuse me, derivatives or antiderivatives that you would need in one book. So this was just the summary of everything. Flame test colors, preparations of reagents, quantities, rules for naming organic compounds, isotopes, just everything you would ever need in any science class was.
Does it tell you how
Right
to
there.
dispose of chemicals?
Oh yeah.
How much did they cost?
This one, there's a price in here, and I don't know if that was the used price. This was 1947. Okay, so that says like $6.10, which I think it was probably more than that. And I don't even remember, somebody bought this at an auction and gave it to me just so I'd kind of be able to show you all like how science used to be done. Of course, my Chem 1 students are going, what's density? Anyway. Nick?
Why did they just make the pages
Germanium
bigger?
happen to be like 5.3 something?
Huh?
Just the density of germanium happen to be like.
Yeah, it's like 5.32.
See, I don't know why can I remember that from Chem 1? Like
You remember that?
Yeah, that's the lab people are doing where they had to find the unknown density of germanium. Yeah.
How long is the index?
Oh, nerd alert.
The index starts. Here's velocity of seismic waves in case you needed that. The index starts like right here, so the index isn't all that
It's a tiny
long.
index.
That's smaller than I thought.
But yeah,
Well, actually, that's a lot of
the index.
pages.
Wow.
So, anyway, there you go. All right, so kind of the ultimate old school type thing. All right, so why it's gone too?
Oh.
Who would have thought? Okay. All right. So here's what I want you to get out of the lab. Okay? Here's some of the main things. So that first graph that you drew should look something like this. You're going to have velocity, meters per second. You're going to have centripetal force here in newtons. That's going to start at 0, 0, and it's going to go something hopefully like this. Okay? That's the quadratic function. So that's the first thing I'm going to look for. Hey, it's labeled, do you have everything? Here we go. More importantly, that you understand why. So this lab is brought to you by the equation that centripetal force equals mv squared overall. Okay, that's the whole point of this lab. So here's what I want you to look at. You have 4 variables. On any of these, you're going to change 2, or excuse me, you're going to keep 2 constant. You're going to change another one, and then velocity will be the equalizer. Okay, so velocity will change to balance things out. So velocity was never constant. Okay, velocity was the value that was always going to be changed to keep these things working. So on trials 1 through 4, the key assumption that you're making is that as that thing is being swung around, the mass of whatever is hanging down is what is creating the centripetal force. Okay? Key assumption number 1. So that, where it says centripetal force column, okay, the first one to the left of the right column, if that makes sense. Or to the column to the left of the right data table. That centripetal force is just going to be the weight of what's ever hanging down. So like on trial number 1, you should have 0.98 newtons. For trial 2, which is 0.2 kilograms, you should have 1.96. Okay? So what's happening on trials 1 through 4, you're making that centripetal force value get bigger and bigger and bigger and bigger and bigger. But you're holding the mass of the stopper and the radius as a constant. Okay? Those 2 values aren't going to change. So basically, what you can do is rearrange this to say, oh, this is centripetal force equals kV squared. Okay, so this k is just a constant. If you're in a math class, this is just a quadratic function that says y equals mx squared. Okay, that's all it is. Y equals mx squared. That's it. Don't flip out. Okay, or excuse me, kx squared. That's k. I was thinking slow. Y equals kx squared. Oh, you see that? That's a graphic function. So over there on page 2, question number 2, where I say, using this equation, which values are changed and which ones are constant. Two of the 4 are going to stay constant, which in this case is going to be mass of the stopper and the radius. And what values did you change? Oh, centripetal force and velocity. Okay, that's it. And then when you answer question number 4, explain that relationship of your graph, you're just going to say, simplest thing you can possibly say is, oh, since mass and radius are constant, as you increase the centripetal force, the velocity has to increase. Okay? That's all you have to say. Don't write your doctoral thesis. Okay? And that's the format that you want to use on the next set of questions. Next ones, you go, oh, what did we hold constant? Oh, we held the mass of the stopper and the centripetal force constant. Okay. We changed radius and velocity. Last one, you changed mass and velocity, and you kept centripetal force and radius a constant. Okay? So that's what I'm looking for on those. Don't make those complicated. But make sure, listen to me, make sure when you have answered questions 4, 8, and 12 that you have mentioned all 4 variables. You have mentioned centripetal force, mass of the stopper, radius, and velocity. So when you read those answers, check them off. Hey, have I used these terms? If you haven't, just don't write them at the end. It's like, oh man, I left out mass of the stopper. I'll just write that at the end. No, it's not going to cut it. Okay. When you get to question number 13, we're going to basically say, hey, how valid of an assumption was it to let us say the centripetal force is what's creating the centripetal force based upon data? So what's going to happen on number 4, you're going to go mv squared over r. You're going to go to the stopper. That's going to be the stopper mass. It's not the mass of what's hanging down. That's your stopper mass. You're going to go to your data table. You're going to find that velocity. Divide by the radius. You're going to get a number. Let's say that you get, I don't know, 4.18 newtons. Okay, whatever it is when you get out, whatever you get when you get out of that calculation. So then you're going to take your theoretical minus experimental over theoretical times 100. And by the way, this is what nerdy science teachers talk about at lunch. We've discussed this today. It's like, okay, is everybody teaching this the same way? Because I looked at some Chem 1 things. It was like everybody was, but they were using different terminology. So hopefully everybody gets on the same page. But that's what we talk about at lunch, is how do you calculate experimental error? So you can take 3.92 newtons, which is the weight of that 0.4 kilograms, minus, in this case, 4.18 newtons, which is what you got from using mv squared over r. So that's your experimental value. And then you're going to divide that by 3.92 times 100. Now this is why it doesn't make any difference how you subtract it, because it's an absolute value anyway. Okay? So typically those errors are between 5 and 15%. Okay, that's typically, they're usually pretty good. Okay? And then you're going to do that for trial 8, and then you're going to do that for trial 12. On 14, you're just calculating G's. You're just going to take your centripetal acceleration and divide that by 9.8 meters per second squared. All that is just a ratio that says, hey, this is what we have. On 15, the numeric value should be a pretty decent GPA, not horrible, not stellar.
Which one?
On 15. So the numeric value is a somewhat respectable GPA. Okay, not stellar by any means, but somewhat respectable. And the exponent should be something close to the legal drinking age. Okay? Not what you think it is during prom weekend when your mom and dad are out of town. Now, when you get to question number 16, so let's talk about the significance of your answer to number 16. Your answer to number 16 should make even a worse GPA than your answer to number 15 is. Okay? So one of the things that they ran into onto this argument about does the Earth spin on its axis. So here you are, you're going around like this. We're sitting on the spinning rock. We can't tell it just because we're used to it, okay? And the question is like, if we're going this fast, and even like, up here in Maze, America, okay? Even where we're at up here, we're not quite going as fast because we're not at the equator, but right now we're going at about 400 and some odd meters per second. But you don't feel it, okay? It's like, you don't get the sense that you're going that fast. But here's the argument, was that how can we have ocean? Why do things not fly off if we're spinning that fast? If we're actually going 400 some odd meters per second, why don't things go flying off? So what you're calculating on number 16 is the amount of centripetal force to hold a 70 kilogram person, which is about 180 pounds, okay, roughly, on the Earth to keep them from flying off. Okay, so in other words, if, let's say, for example, let's say we didn't have a gravitational field. If you were to tie a string to this person, basically what we're asking is that how much tension would be on that string to keep this person from flying off and becoming a projectile. And what you should see is it's a pretty small number. Like I said, it's even a worse GPA than your answer to number 15. What that means is that if you look at the weight of this person, okay, the gravitational force acting on that person, if you take 70 and you round G up to 10 instead of 9.8, you get about 700 newtons. So gravity is providing about 700 newtons pulling this person down towards the surface of the Earth. You only need less than 3 newtons to keep this person from flying off. So gravity provides more than enough force to keep us, the oceans, penguins, squirrels, whatever, from going flying off. Okay, so once they did that calculation, they said, oh, okay, hey, we're cool, you know, we can stay on the earth, that's a good thing, okay? And that's why you have oceans. Now, but here's your odd geological fact. Because the earth is spinning, the earth is actually flattened a little bit on the poles, and it actually bulges out a little bit in the middle because it is spinning. But it's not a huge difference, but it is a little bit flatter on the poles and a little bulgier in the middle. That happens as you get older. Gravity shifts. Okay. All right. No, it's true. It's like Einstein's equation, like E equals mc squared. So when you're young, this is a true story. You'll appreciate this as you all get older. So as you're young, you have a lot of energy, but not a lot of mass. And as you get older, that equation shifts. So your energy changes into mass. So you lose energy and you gain mass. I'm just telling you it's going to happen. So I know you don't want to go with this present work, yeah? It's physics, sorry. Okay. Make sure on number 17 that you have clearly, I emphasize clearly, labeled every force. You write down the numeric value of that force, you draw it with a ruler to scale, and you show me what that scale is, okay? So, if you're not sure if you have all that, give your paper to a friend, say, hey, Bert can't figure out what I have going on, okay? So, if there's a force there, make sure it's labeled, and I know what it is. We're good. Make sure that you have labeled your graphs so that I know which one is which. Okay, don't make me guess which graph is which. Okay, make sure that you've labeled all those. Any questions? Going once, going twice. So stop yonder. So here's what we got today, kind of a wrap up of everything dealing with horizontal centripetal motion. You got an assignment today. Then tomorrow we'll do vertical motion, dealing with centripetal motion. And that's where gravity begins to play into a role. And then that's Wednesday. Then we'll start into Newton's laws, motions of satellites, gravity, that type of thing. After that. So right now, kind of the test over this is looking like it'll be kind of Thursday of next week. Okay? So you kind of want to plan ahead. Now, let me talk about an option. And I'll do this if you all are interested. Because we're going to be starting interplanetary motion, the science department actually wrote a grant to get a really cool big telescope, and we just got it in. And so, like, you've got Jupiter is visible in the east, Saturn's visible in the west. We'll have the moon up. So I was thinking maybe like some evening next week, maybe have get that out, maybe about 7 o'clock. I mean, it certainly wouldn't be mandatory, but if you just want to come up, look at it, it's a cool deal. So I'm thinking maybe, looking at the forecast, maybe Tuesday night of next week. Is that an option? Is that kind of looking like that might work? Maybe about,
Yes.
what?
Yes.
Is that going to be a conflict with volleyball, or you got,
We're done.
okay. Soccer,
That's not funny, Sam.
huh?
We'll play that. No, we will. Potentially.
Well, I don't want, we can do it Monday night.
They're not gonna win. That would be
I'm not.
Sam,
Sam,
why are you so mean?
yeah.
Tuesday's better?
It's realism, not optimism.
Okay, let's kind of maybe right now tentatively schedule for Tuesday night. We'll see what the forecast is, because obviously it's cloudy, that's gonna be a train wreck. So let's kind of schedule tentatively,
No, Sundays are nice.
next Tuesday night about 7 o'clock, we'll just meet here. Maybe we'll make some hot chocolate, you know, so that type of thing. All right, so that's just something to think about. Okay, so what this video shows is kind of the ultimate example of what happens when you lose friction and you're trying to move in a circle. Because remember, when you're talking about centripetal forces, remember centripetal force is not one of the fundamental forces. Why isn't it one of the fundamental forces?
Because it only manifests on negation.
Yes, it manifests itself through something else, okay? There's a strain, there's a gravitational field, there is friction, okay? Something like that has to be present to create the centripetal force, okay? So what you see is this guy's going to be going around and their guy blows an oil line in front of him, and so it puts this coat of oil on the pavement. And so these guys are coming around, and everybody says, well, there's a force pushing them going straight. So just remember, like, you know, if every object that has mass also has inertia, which means it wants to move in a straight line at a constant speed. For lack of a force, you maintain that. So just keep that in mind when you're watching this video clip.
Throttle with a sudden burst of speed. He tries to pass another rider, but the racer's daring move leads to disaster. Taylor wipes out. The bike topples over.
So at this point, notice he's just moving in a straight line until an outside force acts upon him. That's where he got lucky, was that other motorcycle didn't take his head off.
The trouble starts here. Taylor's hitting speeds of 205 miles an hour. He got
On a motorcycle.
Smoke billows. His oil line ruptures. It spreads a slick on the track. Kellner's in a violent skid across the asphalt.
But notice he is going in a straight line.
He slams into a barrier.
Woo!
Then cheats death by only an inch. A different angle shows the incredible
Yeah, Hacks like to be the camera guy. But look at, if the carnage just
With
continues.
such force, it bounces him back to the ground. A lucky break that saves his life. The other riders hit the oil and wipe out.
Notice all of them just go boom, straight.
In all, 7 racers slide into the trap, but no one is seriously injured. In this race, staying alive is considered a win.
Staying alive is considered a win. It's like, who writes this?
How lucky is this guy?
Anyway, all right. So let's talk about a different spin on centripetal motion. So what I have here, hopefully, maybe some of you might have seen this in your Chem 1 journeys, otherwise known as a centrifuge. So centrifuges basically work by creating a very intense gravitational field. So if you've ever seen this, you open it up and there's just like 6 openings and you put test tubes down in there. If you ever operate one, you just want to make sure that everything is balanced. Just don't put one test tube on one side or otherwise it's out of balance and it shakes violently. So it works pretty simple. Then you just close it down, turn it on, and then it starts spinning and spinning and spinning. Gets up to speed. Okay? So at this point, this particular machine spins at about 4,000 revolutions per minute. Okay, so let's talk about what that means. So that spins at about 4,000 revolutions per minute. Now, some of you on your cars, okay, let me open it up. Even then, it's still spinning pretty quickly, okay? So, on your cars, you might have something called a tachometer, which measures, it's the same thing. It stands for RPM, which is revolutions per minute, okay? So, typically, like your car idles at about 1,000 RPM, which means that your engine is making 1,000 revolutions per minute, okay? When you gun it, it might go up to, 2, 3, 4,000 revolutions per minute, okay? So that's kind of just basically indicates how fast your engine is running. So if we want to calculate the centripetal acceleration in the bottom of this test tube, we need some information, okay? So one option is that we can go, okay, well, centripetal acceleration is 4 pi squared r over t squared, okay? So that's an option, we can do that. So the radius from the center of the centrifuge out is about 12 centimeters. So from the center of the centrifuge out to the bottom of that test tube is about 12 centimeters or 0.12 meters. Okay, we got that. That's the easy part. The tough part is going to be this value of t. Now, if you look on your equation sheet, over here on the right-hand side, underneath rotational section, you have this little deal that says period equals 1 over f. Now, period is something that we've talked about. How long does it take that rubber stopper to go once around in a circle, okay? Orbital period of the Earth. Oh, that's 365.25 days. How long does it take for our rock to spin on its axis? Oh, 24 hours. So we're familiar with the concept of t. So technically, period has units of seconds per revolution. We usually don't write in the revolution part because it's like implied, but technically, and this will play out large later in just a second, technically that's seconds per revolution. Now, anybody know what the little f stands for?
Frequency.
Frequency, okay? So frequency has units of revolutions per second, okay? Now, notice that these are inverses of each other. So let me kind of give you a simple example. So let's say that, is there a rubber stopper in the window?
Yeah.
Rubber stopper. Okay, so here's the classic example. So let's say I take this rubber stopper and I swing it pretty slowly, okay? So you all could sit there and you can count, don't get hypnotized by the way. Y'all are dogs. Whew! Okay, all right. So, this, great, you screwed that up your cat now. All right, great. So, this is swinging pretty slowly, right? So, you can time that and go, so if we go 1,001, 1,002. So, that's okay, we get an idea of how long that takes. Now, what I'm going to do, though, is I'm going to make it spin faster, okay? So as I make it spin faster, what happens to the time for one revolution? It decreases. But what happens to the number of revolutions that it makes per second? That increases. So these are inverses of each other, okay? So what that means is if something has a long value for t, okay, that means that, so if you have a big period, that means it's not going to make very many revolutions. But if you make it spin faster, like this, okay, then the value for t becomes small, but the value of frequency goes up, Okay? So this is what I want you to see. These are inverses of each other. So, and the beauty of this is mathematically it's very simple to solve from the other one. So if you want to solve for frequency, I can take period times frequency, that equals 1. So then, a miracle happens, and frequency equals the inverse of period. Okay? They're just inverses of each other. Now, this is where the magic happens. You're going, I don't see much magic. Well, there's a little bit of magic, and that's all it takes in your life, just a little bit of magic. So if I look at the units here, that's 1 over seconds per revolution, because that's what the period is measured in. Oh, look, the revolutions flip up, I get revolutions per second, okay, which is what those units are measured in. So this is why these are inverses of each other. So let me lay out a couple of things that you can do with this. Armed with this little bit of magic, okay, let me get rid of my chemistry lecture. God knows what you'll see on this board in any given day. All right, so let's go back to the idea that our centrifuge was spinning at 4,000 revolutions per minute. So let's start with this idea. Is that frequency or period?
Frequency.
Yeah, because it's an event per unit of time, right? It's revolutions per minute. So we can't deal in minutes, but what can we deal in? Seconds. So I can take, so somebody get a calculator and take 4,000 revolutions and divide that by 60 seconds. 66.7?
Yeah.
Okay? Revolutions per second, which is pretty fast if you think about it, okay? In 1 second, that thing is going around about 70 times. In 1 second, it goes around about 70 times. That's hauling the mail, okay? Now, if you want, now I'm going to show you both ways you can work this problem. How you do this is up to you. It's whatever feels most comfortable for you. So one option is that you go, well, we know that centripetal acceleration is 4 pi squared r over t squared. But here's the problem. That's frequency. I need time. So what can I do?
Use your inverse button on
Oh.
your calculator.
Yeah, so I can take the inverse of 1 over 66.7 revolutions per second. The seconds flip up. I get seconds per revolution. Miracle of miracles, I'm golden. So if you want to go that route, let's go that route. So somebody take 4 pi squared times the radius of 0.12 meters. Now, what do you get when you take the inverse of 66.7?
0.015.
0.015, exactly?
499, a bunch of numbers.
Okay, so we can call it 0. Okay,
Exactly. I got it exactly. Yeah, if you use full values, it's exactly.
it's exactly that? Okay. Seconds squared. Okay? Or you can just take the inverse of 60 and divide it by 4,000 and get that too. So let me know when you get what you get out of this calculation. So take 4 pi squared times 0.012 and divide it by 0.015 squared.
2.11 e to the 4.
What'd you get?
2.11 e to the 4.
2.11 times 10 to the 4th?
Yeah.
Okay? Meters per second squared. Now, out of curiosity, let's talk about G's. So take that and divide that by 9.8 meters per second squared. So we get G's.
2,148.5.
2,100 and what?
48.5.
So 2150
That's a lot of G's.
G's. So what that means, if you're in the bottom of that test tube, your body is going to feel 2,150 times heavier than it does right now.
I can survive.
Now, to give you some perspective, the human body starts to feel uncomfortable at about 2.5 to 3 Gs, okay? Most people will pass out at about 4 to 5 Gs. You break bones at about 20 Gs. So the point of this story is that if you ever are in like the Ant-Man movie and you get shrunk down,
Don't go into centrifuge.
and someone goes to drop you into the centrifuge, don't go. Okay? It's not going to end well. Right? You're basically turned into a little dot, a smear on the bottom of the test tube. Okay? 0 out of 10, don't recommend. Okay? So if someone offers and says, hey, let's go for a ride in the centrifuge.
It's like the teacups.
Huh?
It's like the teacups.
Kind of at Disneyland? Yeah. Yeah. You get spin around like, whoa! Okay.
Where can
But
they
that's an
feel
extreme. Now,
for design?
but if you go, Mr. Burkham, is there another way? Ah. But wait, there is another way.
For what?
So what you could do, and this is a personal preference thing, okay? This is just a personal preference, okay? The other thing that you could do is you could go, well, we know that centripetal acceleration equals 4 pi squared r over t squared. Okay, we know that. But we just said that period is the inverse of frequency. So we could write this as 4 pi squared r times 1 over f squared. Right? All it is a simple substitution. But then we have frequency in the denominator, so what could we do? Oh, we could move that up here and write 4 pi squared r times frequency squared. Okay? But it still has to be in revolutions per second. So the other option is that you just take that frequency. Oh, stop. Times I hate this thing. Okay? So the other option is that you just take 4,000, divide it by 60, and you get 66.7 revolutions per second, and you just slam that right into that, and that way you don't have to mess with taking the reciprocal. Okay? That's an option. And you can do the same thing, that not to sound like an infomercial, but wait, there's more. For an additional shipping and handling, we can do this again. So one option is that you have v equals 2 pi r over t to calculate velocity. It's cool, right? Guess what? You could go, oh, that's 2 pi r divided by 1 over f. And you could write that as 2 pi rf. Okay? Which is the same idea. Okay? Got it? Good? Grand? Okay, stop that for a second. Through some of these problems before you get the urge to, like, assume the fetal position and suck your thumb because you don't know how to do the problem. So let's talk about, and again, separate sheet of paper. Answers on the left, work on the right. So let's talk about number 3. So you got a toy plane into a wire going around. It's made to go faster as more wires played out until both the speed and the radius of the circle are constant at double their original values. We want to look at what's going to happen to the centripetal acceleration. So there's 2 ways you can do this problem. The first decision that you have to make is what are you going to use to calculate centripetal acceleration? Are you going to use 4 pi squared r over t squared, or are you going to use v squared over r? Which one in this case would make more sense? Yeah, you're talking, read the question. What are you talking about? Speed, which is velocity, and radius. You're not talking about orbital period, right? Okay? So, smash mouth physics, so we're going to go with this. So what's an easy velocity that we could use?
1.
1. Okay, and that's going to get squared, and an easy radius would be 1 meter. So oddly enough, that works out to be 1 meter per second squared. You could have picked 10 and 10. Doesn't make any difference. I just picked 1. Okay? Now I want to look at the new centripetal acceleration. So what's going to happen to the speed?
It's gonna increase.
It's going to increase, but by how much?
2. Let's put 2.
It's going to double, right? It says it's going to double. So
Oh.
instead of 1 meter per second, that's going to become
2.
2 meters per second. And that's going to get squared. And then the radius is going to become,
2 meters.
because it's also going to get doubled. So basically what's happening is this. So imagine me swinging this thing around like this, okay? But then I'm going to double the radius, but I'm also going to make it go twice as fast, okay? So that's kind of the scenario that you're looking at. So then, but I got 2 squared, which is 4, divided by 2 gets me 2 meters per second squared. So what's going to happen to my centripetal acceleration? It's going to double, okay? Now, but think this through. What if you just doubled the velocity and kept the radius the same?
The quadruple.
Then it would go up by a factor of 4. Pay attention to that. Now, here's the more elegant approach that you can take. You just sit there and go, okay, that's v squared over r. Cool, standard way to calculate centripetal acceleration. Then you go, okay, well, let's talk about AC prime. Well, that's going to be, instead of v, what am I going to have? 2v. In this case, 2v or not 2v? In this case, I2v. What about my r? This is the pirate's favorite move, because instead of r, we're going to have 2r. Okay? So now I've got 4v squared over 2r. So I get 2v squared over r. Guess what? It gets double. Okay? So I don't care how you work a problem like this. Do smash mouth physics, make up numbers? Do with the elegant approach? I don't care. It's up to you. Okay. Now, when you get to question number, or problem number 7 down below, you want to compute the Earth's centripetal acceleration towards the sun, take the time it takes to go around to 365 days, and a radius of 1.5 times 10 to the 8th kilometers. So basically what we're saying is that here's the sun, here's our rock, we're going around like this. Now there's 2 ways you can do this. One is horribly difficult. One option is that you go, oh, I'll calculate velocity. I'll take 2 pi r over t. You know the radius, you know how long it takes for the Earth to go around, you get v. And then you slam that into v squared over r. God-awful amount of work. It works that way, but I don't recommend it. It's easier if you just go straight into 4 pi squared r over t squared. That way you can just do that problem in one step. If you're really hung up, it's like, no, I really want to know what's the velocity of the Earth as we go around our star. Fine, do it, okay? I'm not saying you can't, but then you got to plug that back into v squared over r. Now, when you're converting those days into seconds, don't round that number, okay? Keep, because that's an exact value. 365 days is an exact number of seconds, so make sure that you pay attention to those units. When you get to number 9, okay, you got a test tube going around, okay, swings out, so that this test tube is swinging around like this, it's horizontal, and you're spinning at 5,000 revolutions per minute. You're at 150 millimeters from the central spin axis. There's a whole bunch of things that you need to calculate with that. You have 5,000 revolutions per minute. Is that frequency or period? That's frequency. When you get to number 10, okay, so here's the idea on number 10. Mustang go from 0 to 60 miles per hour in 5.6 seconds, okay? So that's like a linear acceleration. So let's say that you happen to own, however, a Mini Cooper, okay, which is a cute little car, but it's just not built for speed. But you want to feel the same acceleration as if you were in a Mustang going from 0 to 60 in 5.68 seconds. So basically what I'm asking you to figure out is that How fast do you have to drive that little Mini Cooper around in a circle so that your centripetal acceleration feels the same as the linear acceleration of that Mustang taking off in a straight line? Okay? Now, let me give you my own experience with large G's during linear acceleration. So over the summer, Sedgwick County Cooperative, they're the ones that actually provide electricity to this building and with the solar array, so I've worked with them a lot. So they called me up and they said, hey, Burkamp, we got a new electric truck in here. So if you've ever heard of it, it's called a Rivian, okay? And they said, you need to come out and just drive it around. I said, okay, I can do that. So each tire has its own individual electric motor. So it isn't like you have a transmission. Each motor is individually, or each tire is individually driven. So we pull off the side of the road, and they said, come over, try it. I said, okay. He goes, now punch it. I said, really? You're going to let me do that? They go, punch it. I was like, okay. So I floored it. I had to let off the gas after about a half a second because I was actually passing out. Because that car will go 0 to 60 in like 2.4 seconds. Which is like, yes, I have never in my life experienced acceleration like that. Literally, like my blood was leaving my brain. Okay, I was having like an out of body experience. Like, I'm not kidding. Like I was getting like seeing like tunnel vision. I mean, it was that intense of an acceleration. It has like 800 and some odd horsepower. So, I mean, I have never in my life experienced acceleration like that, ever. And it was like, bam, whoa! So yeah, so it's pretty intense. So electric cars, if you ever drive one, oh my God, woo! Step back, Jack. Okay, anyway, so that's the whole idea on that. I'm done. You have time to work on the assignment.
Let's go.
So stop yonder, camera out.